a little bit better. It's actually, in this case, we can actually do a bit better than the 1,000 that's listed there. But that's not going to be a great plan with this approach. There are several things that you may have noticed that say that this thing is not all that great. One of them is that the selections could have been done earlier, because what we're doing is we're combining every block and every reserve based on SID. And we're not taking advantage of applying the selections early, and we're not taking advantage of indexes. So this would be a relatively bad plan. So the goal of the optimizer is to find, equivalent plans that get the same answer, but are going to be more efficient. Okay, so here's a plan that is going to be better, and it still doesn't use any indexes. We're going to do this little by little. We did this in 180 in a simpler form. We're doing it with more numbers inside 181, and we're going to do a sort merge join in this case. So the key thing is we're going to get rid of the irrelevant stuff out of a table earlier rather than later, and we'll see how to play with this. And there is a general principle that, and I'm going to violate that on a slide that we're going to get to soon, but the general principle is try to push down predicates as far as you can inside the tree so that you don't look at irrelevant stuff. So here's the way it works. So suppose that we just have 5 buffers. Then the cost of the plan would be, well, here's what we're going to do. We're going to scan reserves, and we're going to write the result to the temporary, because we're also going to be writing only the ones that have BID equal 100. Because if the BID, as we go through the reserves, if the boat ID is not 100, it's not going to affect the answer. So why bother looking through if the boat ID is not 100? Everything that has boat ID not equal to 100, you see it, you say, I don't care about that darn reserves. So you ignore it. You keep on going through. Same thing, as you go through sailors, what you're going to do is you're going to write to a temporary only those sailors who have the value of rating greater than 5. And if we assume that there are 100 different boats and that we have uniform distribution of boats, that every boat is going to have 1/100th of the reservations, then what we're going to be doing is we'll scan the reserves. It's 1,000 pages, so we're going to read those. The result that we get, if we assume that there are only 100 boats, we're going to have 1/100th of those pages, which is 10, right? If we assume uniformity, there are 1,000 pages. Every boat has 1/100th of those pages. So we're going to write out 10 pages that correspond only to the reserves that are for boat BID number 100. Same would be true if it was BID 13 or 98 or anything like that. So the cost of that in that case is going to be 1,000 plus 10, which is 1,010. 1,000 to read, 10 to write, bang, you got it. We're going to do the same trick with sailors. We're going to read through all 500 pages of sailors. We're going to write out a 10s. Assume that there are 10 ratings, then half of them are greater than 5, that the ratings go from 1 to 10. So if the ratings go from 1 to 10, if we're making our uniformity assumption, then we're going to end up having 5/10, which is 1/2 of the ratings being greater than 5. So we're only going to get half of the pages. So we're going to have 500 to scan, 250 to write out only that half of the sailors that have rating greater than 5. That's going to be 750. And now what we're going to do is we're going to do a sort merge. Everybody remember the formula for the cost of doing a sort? The cost of doing a sort merge is going to be the cost of sorting R, sorting S, and merging them together. So the cost of doing a sort is going to be 2n, or that's the number of pages in the relation, 2n times the number of passes. What is the number of passes? Log to the base b minus 1 of n divided by b, where n is the number of pages in the relation. Let me say that again. We spent time on the sort. You may or may not remember it, but the cost of doing the external sort, using the approach that we described, is going to be 2n minus the number of pages in the relation, times log to the base b minus 1 of n divided by b, where b is the number of buffers that you're working with. Okay? So, you know, trust me, I mean, basically, in this particular case, because you end up having T1, which is 10 pages, it's going to be 2 times n times the value 2, which is going to be log to the base 4, log to the base b minus 1, log to the base 4 of n divided by b, where again, n is equal to 10, b is equal to 5, so again, you're taking the ceiling of that log, so that's going to give you the result 2 times 10 times 2, and that gives you 40. Same deal, when I'm sorting n2, it's going to be 2n, n is 250, number of pages. It's going to be 2n times log to the base b minus 1 of n divided by b, and that's going to be 4. Not hard to figure out. Again, b is 4, and in this case is 250, bang, that's where the result comes from. Okay, so that's going to be the result, that's going to give you 2,000. What's the cost of doing the merge? Assuming that you don't end up having, you know, something unreasonable, this cost of doing the merge, we're going to assume is going to be something where you know, basically, we're going to scan through R, we're going to scan through S, unless there end up being lots and lots of matches, you're going to end up having something where you scan through R, you scan through S. Yes, you'll sometimes have to go back because the same S group is going to have to be touched a lot of times. But if we make the assumption that the S group is always in memory for all the R tuples that match it, so the value 98 appears, you know, a bunch of times in R, 12 times in R, 100 times in S, we'll assume that the S group of pages is going to be in memory each time. So we scan R, we scan S, we're going to find the S matched pages in memory all the time. So it's going to be basically the size of R, the cardinality, the number of pages of R, plus the pages of S. You got where that assumption comes from? They're assuming that we're not going to have to go back to bring in the S matches because we just touched them and they're still going to be in memory. So the merge is going to be 10 plus 250. And you add that up, right? So it's going to be 40 plus 2,000 plus 2,500, which is going to be 4060. That's going to be the IOs. And you know, if you work out what it's going to be with a block nested loop join, it might be something like 10 plus 10 times 250. Maybe you could do a little bit better because of the hashing. So that's going to end up being 4270, which with that assumption is going to be a little bit worse. So the 4060 looks better, although it's the same kind of order of magnitude. But you may have noticed that we can do better using a gimmick that, again, I briefly discussed in 180. You only care about certain attributes. Now, there aren't that many attributes in sales and reserves, but as I've told you, there can be situations where you have tables that have hundreds or even thousands of attributes in them. In SAP, there were tables that had 1,000 attributes in them, not just in SAP. So, when I wrote my temporary, why did I have to write out all the attributes that I got out of reserves? Why not just look at, just as I can say, I only want relevant tuples, I also only want relevant columns, relevant attributes of these tables. So what I could do is say, for T1, after I've checked the things with BID 100, the only columns that I care about in reserves are going to be the SID values so that I can do the join. Nothing from reserves shows up in the answer, just the serial number. So why am I keeping all the attributes around when I only care about one of them? So when I write out the temporary, I can make that smaller, which is going to seriously reduce the number of pages that I have in the temporary. T1 can be a lot smaller than what I said here. 1/4 the size, maybe less. Same thing, when I'm writing out sailors, I will care, after I find only the sailors whose rating is greater than 5, the only thing I care about is the SID in the name. And I don't care about the rest. So when I'm creating the temporary, I can reduce that down, so you know T1 is only going to fit inside, it's only going to take 3 pages, let's say, and so on. T2 is going to shrink down as well. So again, the costs get smaller by taking advantage of that thing. Relevance ends up being really important. Okay. Now let's see what happens when we end up using an index. And by the way, I edited this slide actually today and reposted it, changing the purple comments on the right, because the purple comments on the right were wrong before. So there are 2 purple comments, the ones next to reserves and sailors that were wrong before, and I think they're right now. So notice that that editing has been done if you downloaded this lecture. So we're gonna use another plan with indexes, and let's assume, we're gonna make things pretty for us now. Let's assume that there's a clustered index on the BID column of reserves. And let's assume that there's and so a clustering B-tree index. And we'll assume that there's a hash index on the SID column of sailors. Now remember, the indexes don't have to exist before you start executing the query. There are optimizers, and not just a few of them, that may choose, particularly for expensive queries, to create access paths before they begin. And so if I don't have this access path, it's going to be expensive. It'll take me a little while to create the access path, but once I've created it, it takes me, $500 to create the index, but I reduce the cost of executing this query by 2,000. So I'll bother creating the index because it'll save my cost of executing, and maybe when I'm finished executing my query, maybe I'll throw out the index, maybe I'll keep it around, maybe I'll throw it out. It's one of these difficult decisions to work out. But you have a choice as to whether or not you create indexes even before you start processing the query. You don't have to take the world as it exists. You can change it for yourself. So here we're going with two really optimistic assumptions. The one on the left is very optimistic. The one on the right is less optimistic. Having a hash index on SID is, pretty good idea. It's a primary key anyway. Why not? And I don't usually look for ranges of sailor IDs, so I don't need to, have it be a tree. I'm looking for all sailor IDs between, 1, 2, 3, 4, 5, 6, and 4, 5, 6, 7, 8, 9. No, I don't do that. Maybe you do. I don't. You're welcome to. But usually, it's a hash index on SID could be a really good idea for primary key and so on. So we'll assume that there's a clustering index on boat ID of reserves, which means that I can get to all the things with the same boat ID together. They're in the index. They're together. I only text the pages that I care about. So basically, there are 100,000 tuples inside reserves. I'm assuming uniform distribution of 100 values. So basically, there are going to be 1,000 tuples that have boat ID equal to 100. The same would be true for boat ID 13. Nothing special about 100 here. Boat ID, there are 100 different values. That's special. But each particular boat ID is going to be exactly 1/100th of the tuples. So there are 1,000 tuples that I have for reserves that have boat ID 100, right? And so since 100 tuples can fit on a page, that's going to be 10 pages. I just have to read in those 10 pages. So great. Now what I'm going to do is every time I get one of those tuples on those 10 pages, the 1,000 tuples on those pages, I'm not going to bother writing out the result. I won't. I'm going to look through all the reserves that correspond to boat ID 100. I'm not going to write out a temporary. I'm going to pipeline. What does pipelining mean in this case? Not trying to deal with oil reserves in Wyoming or anything like that. What it has to deal with is every time I get a tuple, I'm going to move that tuple up to the next operation without necessarily having to write anything out. Because I can use it to do the next thing up in the pipeline. The pipeline is the tree. And so what I'm going to do is I'm going to get the matching sailors. How am I going to get the matching tuples? Again, I have my hand around the neck of a tuple. For that tuple, I know what the sailor ID is for that tuple, which corresponds to boat ID 100. I know what sailor I'm looking for, because I want to get that sailor's name. I can't get the sailor's name out of reserves. Reserves doesn't have the sailor name. So I find the matching sailor. How can I do that? I have a hash index on the SID attribute of sailors. So I have one tuple out of my, 10 pages worth, my 1,000 tuples out of reserves. I find the matching sailor. I get that sailor's name. But by the way, I check to also see, and this gets kind of interesting, I check to see whether or not the sailor's rating is 5. So I get that sailor using the hash index. And then having that tuple, I check to see whether the rating is 5. And then I output that sailor's name. And so, basically, that ends up giving me the answer. Moreover, by the way, there is at most one matching sailor tuple because SID is the key of sailors. So there's exactly one, or there could be 0 if something was reserved by a sailor who doesn't exist, if I don't have a referential table. Okay, now here's something which is funny. I said pushing predicates down is almost always good. You know what? I'm using my hash index rather than trying to apply the predicate rating greater than 5, because my hash index gives me the matching thing. If I were trying to apply my rating predicate, I wouldn't be able to take advantage of my hash index. I'd have to, go through. I mean, if I had an index on rating as well, I might do index intersection. But it's pretty darn easy to just grab the matching scalar tuple and then check to see whether or not the scalar's rating is greater than 5. And the cost of doing that is basically going to be 10, because I have my clustering index and reserves. I only touch the 10 pages once. And for each tuple, I'm going to have to get the matching scalar's tuple. If we assume that the hash thing takes 1.2 IOs to be able to do, for each of the 1,000 tuples, it's going to be 1.2. I'm down to 1210. 1210 is better than 4,000 and change. And this is just for a two-way join. So in this particular case, things got a lot better than they had been. Okay, so I want to summarize this, and we're going to get back into more costing-related things in the next lecture, which I have already posted. I actually thought I would get to it, but it was important to go over this in time. It'll allow us to go quickly through some of the early parts of the next one. Lots of alternative ways of doing each individual operator. We're going to be spending more time on costing of joins, and then we'll go over a lot of other relational operators after that. So you take the tree of operators and you evaluate the operators in the tree. You can, in trees, do things in parallel. I mentioned there's bushy trees. Just to mention that right now, and I'll mention more later. If I have a join which is A, B, C, D, I could in parallel join A and B and also join C and D, and then combine those two together. So there's a lot of opportunities, many more than I'm describing right now, which we'll get to when we get to parallelism near the end of the term. There are many opportunities for parallelism in query processing, which are used like crazy these days. A database administrator, whether it's human or a autonomic robot optimizer, has to understand optimization to be able to do things well. If you basically, here's the thing, and I wrote Todd's paper back in the 1980s on something that I did research at IBM, which became an IBM product, for being able to do optimization. Suppose that you figure out a really, really, really good index or set of indexes for execution, and the optimizer can't find it. Right? There's something really clever and the optimizer doesn't find it. I'll give you two things about that are interesting. Number one, you haven't done anything useful if the optimizer isn't going to be able to find it. Number two, there are variations of systems in which you can tell the optimizer what to do. And if you're right, then you're telling the optimizer what to do, and it's clever. And by the way, the trouble is that things change, and if you tell the optimizer do it this way, and it's terrific today, and it's not so good a year from now, and you're telling the optimizer to do it, mixed thing with respect to that. Anyway, there are two parts to optimizing a query. Besides transformation, you have to look at the set of alternative plans and do some heuristic pruning of the space because it's too huge. Estimate the cost of each plan that you're considering, including the size as well as the cost, as I mentioned, because size of part of the plan goes into the cost of the next part of the plan. And key things involve the statistics and the different indexes that exist and the order in which you access the tables and all the different optimized operators that you have and how they can end up being implemented, because there are lots of different ways. Here's, as usual, my coda spelled with an A, an added musical piece at the end of this. The original paper by Pat Selinger, Access Path Selection in a Relational Database System, which appeared in 1979, is the classic paper describing optimization. A lot of the stuff in our textbook is based on the ideas that are in that original, great paper. Pat Selinger was an IBM fellow, and she actually recently retired. I mentioned Götz Greffi. He wrote a paper which is moderately hard to read. There are various Volcano and Cascades papers. They're all hard to read, having to do with an approach called Volcano, which was used, Tandem used Volcano Optimizer, so did Microsoft. It had a lot of later influence on how things are doing optimization. Götz wrote a survey paper back in 1993 about query evaluation, which again is probably a lot easier to read than the Volcano papers, so you might take a look at that. But later on I will be pointing to some slightly more modern research that's going on in this. And I will emphasize there's a lot of stuff going on with better statistics and even with learning optimizers, trying to use deep learning to figure out how to do optimization. And I actually have 7 minutes left, so I will get started on the next lecture. These two really should be combined into a single lecture. Definitely should have done this term because there's enough redundancy between them. But I think you'll have a lot of fun when we get to hash fun. Hash fun is a really fun algorithm. But before we get to that, we're going to again go over costing formulas in a little bit of detail. And I will switch over to that lecture. And this allows me, I expected to get to this a little bit faster than I did, but it makes sure that I can give you some fast reminders, which I want to do as soon as the thing comes back. Reminder number one, there's a project that's due Thursday. There were a lot of questions, some of them really, really good. Not of all of which were answered in the assignment. I gave you a whole bunch of hints about this question about forwarding addresses and how to deal with it. There are a number of different ways of playing with it. And so I gave you a lot of reminders about that and scanning. There were a whole bunch of other good questions, some of which were asked privately. And so I posted something yesterday, which I hope everybody reads, that just gives you information about a whole bunch of different issues. For example, this question about what does a scan mean when there might be changes that are going on. In a real-life system, isolation and dealing with that is a headache and a half, especially when there are multiple access paths. It's really important. It's really challenging. This is a very simple-minded assignment. You can assume that there's only one thing going on at a time. I'm not asking you to deal with multi-threading. So, basically, you don't have to really worry about if you're doing a scan, just do your scan, and if things have changed underneath you somehow mysteriously because another student is on your team is changing the data, you're going to know that you're not designed for multi-threading. Don't worry about it. In practice, you really would, but believe it or not, this is hugely oversimplified compared to a real database system. So project 2 is due. You know about the project 1 scores. If you have questions about them, please contact Saloni by next Tuesday, which is tomorrow. We will take comments about it. You don't have to have your questions answered, but they have to be asked no later than tomorrow. We can't take questions. There have been cases where people have asked questions about lab 2 during the last week of the course. It doesn't work that way. There always have to be limits. Sometimes I've asked about lab 3, after the final scores are in, so it always have to be finite. A week from today, there's a midterm, and I posted on the a practice midterm from last year. Probably tomorrow I will post the solution to that. We've gone over most of the material that potentially would end up showing on the midterm. So again, anything that we go over including this lecture that I'm starting, could end up being on the midterm. But there won't be any material past lecture 9. So again, the stuff inside lecture 9 and anything before it could be, but nothing after that. Although we might get to some of that stuff late in the week. So that'll be there. And again, cheat sheets. No cheating, except you can bring in the 8.5 and 11. You can't bring in the electron microscopes, magnifying glass. You can't bring in a friend to read it to you. You have to go ahead and do it yourself. You can prepare the sheets yourself. And you always know which lectures, which parts of the textbook we're going over. So what we're going to be doing is going over, COD's original operators with sigma pi, the join and set difference, the union. We'll also be talking about aggregation and group by. COD didn't have those, but it's an important part of the system. And what's important is that when you take relations and you put them together, you still get relations, and that's really, really vital. So after we cover costs of operations, we'll also talk about how you figure out costs of combined things where you have combinations of operations. That, again, gets kind of complicated. So you are here now where the purple arrow was located. We've started already talking a lot about joins, and we're going to say more about them. You know all about this from the previous lecture. That hasn't changed. You know all about this, not only from last Friday, but I reminded you about it today. Again, emphasis. When we talk about joins, there is a notion of theta joins. You can. We even saw this with the avatar example that we had in one of the first queries we discussed in 180, where we wanted to find all the movies whose length was longer than the, whatever it was, the 98 movie Avatar, whatever the year was, I don't remember. You know, sometimes you do things where you're combining two tables together and the predicate might not be equality. In 99.9 of the cases, 0.9% of the cases, it is an equijoin. So that's really, really important as a focus. It's not the only case, but it's ridiculously important. Doing a Cartesian product would be hugely inefficient. Even if you look at a query, and I've seen customers who've done this. There are cases where people do things where there's a less than or a less than or equal to it. The trouble is, these are really hard things to optimize because, again, you don't get the full Cartesian product, but boy, you get close to half of the Cartesian product if you think about it, if you have something with a less than or equal to. I mean, it's huge. So in our examples, R is reserves, R stands for reserves, C is for cookie, R is for reserves, S is for sailors. That's good enough for me. So again, we assume, you know, pages, TPP, and card, as opposed to the notation in the book, which is incomprehensible. Same thing, you know, for S. And we're going to look at more complex join things other than equality later, but we're going to focus on equals. And again, a critical thing here, and it was even true in the other lecture, we're not going to worry about the cost of outputting the result. For one thing, because you might be pipelining as you go forward, but there is a cost of outputting the result if you have a final answer. Final answer, please. Who wants to be a millionaire? Well, who wants a million tuples in your answer? The cost of outputting the result should be counted. We're not going to be counting that. That's another oversimplification in what we're going to be doing. So, you know what the numbers are. We went over this again. That's the revised notation. I have a funny comma there that I'll get rid of before the notation. I have no idea how that got there. We went over this again at the beginning of the lecture. We've gone over that twice. The simple nested loop join, tuple by tuple by tuple. We ended up saying that there's a page-oriented version, so we looked over that. We went over this twice. We're not going to do it 3 times. We went over how things work with an index twice. We're not going to do it again, so we saw what that thing was. We went through examples, but basically I will spend the time going over this one because we're going to have a focus on costing here. So basically, if we end up having something where we have a hash index on the sailor ID, what you could do is you could go ahead and I think I'm actually out of time, so I'll tell you what. Rather than try to go through this, again, I'll be reminding you about algorithms, but we'll be going over the cost again. I really should combine lectures 8 and 9. And we will get to what I think is one of the more fun algorithms. I hope you've liked some of them a lot, but we will get to the hash join, and the textbook even tells you about more variations of hash join that we're not going to go over. But please look at the textbook and the slides in advance. It really will help you understand what's going on. To be continued.